So today we're going to be looking at the concept of displacement and the concept of distance and how they differ. And I'm just going to briefly talk through how they're used in physics to calculate speed and velocity. So without further ado, let's have an example. So we have a planet here and we have just a standard orbit. Now it was drawn pretty quickly, but I think you get the idea. So let's say it starts and finishes in the same position. So, what is its velocity then? It's actually 0 meters per second, believe it or not. And that's because velocity is a vector quantity, meaning that it requires both direction and magnitude. And because it essentially finished where it started, there's no direction to displacement. So therefore, we've basically got a velocity of 0. However, if we were to talk about speed on the other hand, then of course the speed of it could be basically 8 kilometers per second in orbit. And the reasoning behind this is speed only relies on magnitude. And essentially, because we're not relying on direction, it doesn't matter where it starts and stops. It's just the distance that it has traveled. So let's have a look at basically why we would get 0 velocity. So if we have a look at the mathematical formulae, distance traveled over time is essentially how we calculate speed, or should I say average speed. And by doing so, we're essentially just taking how far the object has gone. In this case, it's done a whole rotation of the Earth from an orbit, and we're just dividing it by how long it took to get to that orbit. So of course, we're going to end up with a figure that is not 0, so it's going to be greater than 0, of course. And for the next one, where we actually look at velocity, or average velocity, which can be represented as V average like that, we are looking at what's known as displacement over time, as I said before. And because the displacement is basically a vector quantity, just like velocity, we haven't really moved anywhere. So we've moved 0 in a direction, because displacement requires direction. And that took us however many times to get round. And of course, 0 divided by anything is always going to be 0. So that's why we have no velocity when we're actually talking about rotating the Earth from the same starting to finishing position. So that's actually quite interesting there. And that's something that is probably a good idea to get your head around, the difference between a vector and a scalar quantity. So when we're talking about velocity, we always need to specify a direction of travel. Whereas with speed, we're just talking about, how fast it's gone in general. No real direction matters at all in that particular case. So, let's just have a look at a 1D example of this. So let's say we have moved 16 meters to the east and 4 meters to the west. Of course, that's not to scale there. Let's say we wanted to know what distance traveled was first. I'll probably do that. Distance traveled is really easy because it's just the combination of those two and we don't need to worry about direction. So therefore it'd be 16 plus 4, which equals 20. And because we always have to specify units, it's 20 meters. So if this took us 3 seconds, then we'd be able to deduce average speed really easily by, of course, doing distance, 20, divide by 3. And that works out roughly to be 6.33 meters per second. It depends how many significant figures you want to go to, seeing as though the greatest one there is basically 14, you could just go to, or is 4, sorry, you could just go to one significant figure, meaning 1 meter per second is the average speed. But now, what if we want to know velocity? So of course, we're going to need to look at displacement now. And displacement is essentially going to be how far we are from the origin, the point at which we started. So we move 16 to the east, and then 4 back to the west. Where do we end up? Well, if this were to scale, it would look a lot better, but we basically end up moving 12 meters to the east, of course. So our displacement we could represent as being 16 take 4, because we moved 16 to the east, and then we basically took off 4 when we moved back to the west in the opposing direction. And then we get 12, but of course, displacement requires units and direction. So we have magnitude with a unit there, and we need direction, which is basically going to be east. And we can represent that as a bearing of 90 degrees to true north. 90 degrees T, because basically north would be up there, and we form a right angle with east there, or if that's true north. So there we have it, that is displacement, and if we wanted to actually show that in a formula, we would basically just do average velocity, which we could represent as being v average, and that equals distance, which is s over t, and therefore the average velocity is equal to 12, and again, I said if it took 3 seconds, 12 over 3, which equals 4 meters per second for velocity, 4 ms to the negative 1. And there you have it. Now you're probably just wondering, this is a bit of a fun side note, why is it ms to the negative 1? Well, it basically means meters per second. And as you can see here, the seconds have been divided by 1. That's basically, well, have been divided, and that's basically why we get meters per second to the negative 1, because s is to the negative 1 within that example. It's just like with acceleration, which I'll go over in a few episodes' time, it's meters per second, which is meters per second to the negative 2. So that's basically all for this week. I hope I've taught you the difference between velocity and speed, and displacement and distance. Remember, distance is how far you went, displacement is how far you are from where you started, speed is distance travelled over time, and velocity is, of course, the displacement over time. So I guess next episode we'll be looking at calculating displacement with 2 dimensions. Thank you very much.